Hello everyone, welcome back. So this time we're going over relative motion analysis for acceleration. Acceleration is going to be fun. So why are we doing this? Because we want to find the acceleration of a point on the body based on its translation and its rotation. I want to be able to do this using relative acceleration analysis. Now it's going to have very similar steps to our velocity analysis. However, we're going to get some extra components in here because the acceleration is going to have a normal and a tangential component. So, for example, in this mechanism for the window, link AC right here rotates about a fixed axis through C. And AB undergoes general plane motion. It's both moving, it's translating, and it's rotating at the same time. Now, since point A moves along a curved path, it has two components of acceleration, while point B, sliding in a straight track, has only one. It's going straight up, that's it. So the components of acceleration of these points can be inferred because we know their motion. We can tell exactly what direction they're going, even if we can't tell exactly what their magnitudes are quite yet. So, using this, how can we determine the magnitudes of this acceleration? What are we going to do to figure that out? Or, for example, if we look at this automotive engine, the forces delivered to the crankshaft and the angular acceleration of the crankshaft depend on the speed and acceleration of the piston, right here. So how can we relate the accelerations of the piston, that connection rod, and the crankshaft to each other? How we tell what the force being delivered or the acceleration being delivered is based on some particular load caused by the piston. Well, we're going to figure that out today. So the equation relating the acceleration of 2 points on the body is determined by differentiating the velocity equation with respect to time. So this first one is pretty basic. We have our linear velocities. And so we're going to get the absolute accelerations as a point. That's just the translation. The second term, though, is what's based on the rotation. And since it's rotating around a curved axis, it's going to lead to a tangential and a normal component of the acceleration, which comes out to be this. Now, this first one, that's the translation. The second one, that's coming from rotation. The first thing we can realize is that that tangential component is simply going to be my angular acceleration crossed with my position vector from the point it's rotating around. The relative normal acceleration, the normal acceleration, is going to be equal to my angular velocity squared times my position vector. If you're wondering why it's negative because normal is always pointing out and this one is pointing in. And the second thing, where does this come from? Well, that comes from our v squared over r. That looked like a v. There you go. Now it's a v. And we have to remember that v is equal to my angular velocity times my position vector. So it's effectively equal to omega squared r squared over r. That cancels, and we're brought back to this equation right here. Okay, so now we have an equation for relative motion analysis. We have this equation, and we're going to solve it using the same steps we've done for relative velocity analysis. And you also need to realize that that's a scalar right there. It's not a cross product. Okay, this is cross, this is not. So how would we apply this? Well, normally what you do is you figure out the acceleration of various points. Like, for example, point A is not moving, but we know that this acceleration right here is going to have a tangential component and a normal component. If we can solve for those based on the angular acceleration and angular velocity, we have the acceleration at point B. Also, since C is in a linear track, it would have to be going to the right. That's its acceleration right there. So we know both accelerations. And if we have the velocity, or so if we have the magnitude of one of those, we can use our relative motion equation to solve for the rest. And I kind of jumped ahead of myself. Okay, so what's our procedure for analysis? I'll go ahead and show all of it. First off, set up a coordinate system. That's always helpful. Then draw your kinematic diagram of the body. I hated this at the beginning, but it's actually very, very helpful now. So draw the direction and sense of the acceleration for every point that you can tell. Then indicate it on all these values and set up your normal and tangential components if you need to. Finally, you're going to apply the relative acceleration equation and solve. You'll break this up into scalar components of this equation. Those scalar components, the I components and the J components, would have to be equal to each other. And then from that, you can solve for any unknowns like the angular velocity perhaps or the angular acceleration to get your final answer. And that would be it. So yes, next time we're going to jump straight into an example so we can show off how to do this. And then we'll learn a little bit more. We're actually breaking it up just a little bit this time. So thank you for watching. I hope this helps you. And I'll see you all soon as we actually put into practice our relative motion analysis for acceleration. Have a great day.